Hello and welcome to part 1 of Dev Maths and Statistics Refresher Course, Lecture 4. In this lecture the topic is linear algebra, which is very important for modelling and statistical analysis in a range of social sciences such as economics, quantitative sociology, impact evaluation and so on. There are two main areas we're going to look at in terms of theory, which are vectors and matrices, and then we look at the application to simultaneous equations. As we'll see in later lectures, you can also use this for optimization, which is a very important reason for us covering it. So if we turn first to vectors. So if we're looking at, for example, economics, we might have a simple model, as you've met in previous examples, where we're talking about the price of a good, the quantity that we're producing, and the time it takes to make it, and so on. However, when you want to do analysis of real societies in the real world, there's a big problem in that there's not just one price and one quantity. There are many, many different things going on. So for example, if you used P1, P2, P3 to talk of all the different goods in your society that you're producing, and then Q1, Q2, Q3, T1, T2, T3, then you might start getting into the welfare level of each individual, W1, W2, W3. It would just get crazily complicated. So, one solution which we use here with vectors is we still stick, instead of putting these numbers in, we still stick with a single symbol such as P, but we understand that that refers to a whole list. So it's a shorthand, and that's called a vector. So a vector really is a shorthand for a list. So let's look at some examples of that. Okay. This just loads the commands into Maple for doing linear algebra. Here we actually define some vectors. So vectors U and V and W are all called column vectors. So you've got 3 different column vectors. Vector R is a row vector. Okay. So you will see some row vectors, but unless otherwise stated, all the vectors that we're going to meet on this course are column vectors, unless otherwise stated, and they're more common. Now this gives us something useful, a short way of saying something. I can say, oh well, the utility of consumers in this situation was U, just U, and that could refer to 4 people at once. So I could say, if this is my vector U, if I say the utility of consumers was U, it means that the first person had utility 2, the second person was very happy, utility 6, third person, 0, and the fourth person was really unhappy, -1, perhaps really suffering. Now, let's turn to the maths. Once you've got vectors, you can add them, subtract them, multiply them in the usual ways, and you should be able to do this easily by hand. So here's a few examples, and hopefully you can see how this happens. So what we've got here, this is U and V and W for reference, 3 vectors, and here is U plus V. So hopefully you can see how you get U plus V just by adding these numbers together. So that's the first 2. If I do U subtract V, you get this. So that's 2 minus 7 gives you -5. 6 subtract -5 gives you 11, and so on. So you can add vectors, you can subtract vectors. Here I'm going to take vector U and multiply it by 4. So it's not surprising what we get. Each number is multiplied by 4 to get 4U. Here I'm going to take R and write it. So that's R and that's 10R. So you can do the same thing with a row vector. You can also divide things by numbers. So that's vector W. This is vector W divided by 6. So just divide each number by 6. Then you can have combinations like this where this would be 2U minus 5V. And just note that you could write this algebraically. This would be 2U minus 5V. Would appear like this. Again, there's vector U, there's vector V. You should be able to check this is 2U minus 5V for it. For example, if we take the bottom one here, so 2 times this is -2. Minus 5 times 0 gives you -2. And you can have things in brackets like this. So you should be able to check that works out correctly. So this is U u take away 2v, and then multiply the answer by 6. So you can do all that sort of stuff, so it's quite straightforward. Whoops. And then here's u, and here's w, and here's u plus w. Ooh. Okay, remember pink means error. And this is u, and this is r, and this is u plus r. So it seems that the computer cannot do this. So why did these not work? Well, even though it all seems very easy, this is impossible because you cannot add this to this because they have a different number of rows, and you can't add this to this because this is a column and a row vector. So when you add two things together or subtract them, they must have the same size. It's called the dimension, same number of rows and same number of columns, and these have got different dimensions. Sometimes if you have a column vector or row vector, you need to turn it into the other form. So this is called transposing. So u is actually the transpose of vector r. You see that that's u, and that's r. This is the transpose of this, and this is the transpose of this. And you just write it as with a dash. Sometimes it's written like this, or some textbooks actually put a little t for transpose. So watch that. It means the same thing. So this is u, this is r, and this is r dash, the transpose of r. And you can see it's the same thing. Okay, now think carefully about what we just did. We have done vector plus vector addition. Okay, addition of vectors is okay. We have done vector subtract vector is fine. We've also done multiplication and division, but we only did multiplication and division of vectors by ordinary numbers, which are known as scalars. So up here, when I started to multiply the vector, I was only multiplying the vector by 4. An ordinary number. These in linear algebra, a simple number is just called a scalar. It's multiplying by a scalar, dividing by a scalar. So far, what we have not done, we have not multiplied a vector multiplied by a vector. We have not done this. Now, in fact, there are several different ways to do it. The only one that I know that's commonly used in social science is called the scalar product. I've also included, in the visualizations for today, I've included a cross product, which is sometimes used. There are other ones as well. Now, the dot product, or the scalar product, is called the scalar product because the answer you get is a scalar. The dots product is called dots product because it's shown with a dot. So u and v, these are the two vectors. Okay, what we're going to do is work out the scalar product, also known as dot product of u and v. Now, hopefully you can see, just pause if you do not know the answer to this, pause the video for a moment and see if you can find how is this, if this is u and v, how is this calculated from these two vectors? You should be able to work out the answer, I think. So hopefully you paused it or you know the answer. So this is how it's calculated. If I can open this section. Calculation here is just 2 times 7 plus 6 times minus 5 plus 0 times minus 6 plus minus 1 times 0. And then you add all these together. So you multiply these and sum the answers and you get minus 16. And this gives us a really useful shorthand because imagine you've got the elements of the vector A are this long list, potentially long, of numbers. Vector B has these elements, potentially many of them. The scalar product is defined as a1, b1 plus a2, b2, all the way up to an, bn. But we can write all that stuff just as a dot b. So it makes it much, much shorter to write down a whole list of calculations, which is why we use it as an optimization, and it's why, for example, Einstein used it extensively in his calculations and theories of relativity. Another way of writing a dot b is it's a shorthand for sigma ai bi, which we'll meet in the section on statistics. So anyway, now you've got the dot products, you can calculate things like this. So v dot v, that's v dot v. This will be written, by the way, as, if you have a vector v v dot v, you could write this as v squared. You'll see that sometimes. So a vector times a vector, you can write a vector squared. So that would be 7 times 7 plus negative 25 times plus negative 5 times negative 5, etc. So it's the square of each of these is 110 when you add it up. And you can write things like this. 3 times u plus v all times v. You should get, if you calculate it, you should be able to see that comes to 62. Okay, but before we finish this first section on vectors, we come to visualization. And this is really useful, particularly for the optimization side. When you have 3 components, you can picture it in 3-dimensional space. I don't want to worry you, but some of the vectors that you'll be looking at will have maybe 15 components. So you really have to imagine how that's going to look in 15-dimensional space. I might ask you to draw that on the whiteboard. But for now, we'll stick with 3 components. So if we take 3 vectors like this, so x and y and z, and then we can draw these in 3 dimensions like this. So hopefully you should be able to see these 3 vectors. So here's the x-axis, the y-axis, and the z-axis. So your job now, if I put it into a position you can see, oh, that's interesting, yes. If I put it into a position of C, you can see, you should be able to tell which one is the blue one, which is the red, and which is the green. So if you want to look at that, just I'll move this around for a moment. Fast forward if you're getting bored. I just want you to have a look and see if you can tell me which is the green and which is the blue. Okay, so you should be able to see that this red one here seems to have an x value of about 5 and a y value of about 1, but the z value is 0 because it doesn't go up or down. So 5, oh, yes, and in fact it's not 1, the y value is -1. Let's go back to here, so that's this one. So x is the red one. This 3, 4 minus 1, that's going to be the green one because it's x is 3, y is 4, and it goes down to z equals -1. So the green one is y, and the blue one must be z. You can see that because it goes all the way up to z is 5, x is -1, so it goes slightly backwards this way, and y is just 2 actually, yeah, 2, surprising. Okay. The next important concept you can get from looking at this diagram is the angle between the vectors. But I'm going to go on and discuss that in the next video because this one's getting too long. So for now, thanks for watching.